Hello. All right. We're doing something pretty cool today. So, last time we basically finished implementing a neural network that, after about a minute of training, is able to recognize handwritten digits with 97% accuracy. So you can see it going here, where I don't know how many seconds, like 15 seconds, 20 seconds into training, we're at 96.6%. After 30 epochs, that's going to be about 30 seconds. Actually, that was a little less than 30 seconds. We get to 96.7% accuracy. And so last time I said we've only read half this book to get to this point. Last time I said I'm going to read the other half and see if there's anything to learn from it for building an LLM, and I don't think there is. So to quickly summarize the chapters that we didn't read through together, this chapter is a proof that neural networks can compute anything. So it shows how you could approximate any multivariate function out of a neural network with sigmoid neurons, and then it asks you to do some exercises to prove the same thing with ReLUs and other types of neurons. This chapter, why are deep neural networks hard to train? The summary is having layers makes things harder. Having deep layers makes things harder. Obviously, deep layers helps you learn more complicated features. Or intuitively, it seems like that's what it should be doing. But you end up with this thing called the vanishing gradient problem, where the gradient of, or I guess hidden layer 1 of this neuron depends on all of these neurons and all of these neurons and all of the neurons in future layers. So it's really hard to figure out how this neuron should change. It's easier to figure out the gradients for the neurons in the final hidden layer than it is for the layers before that. And that's called the vanishing gradient problem. And then the last chapter is about how to do deep learning in spite of the fact that it's harder and harder to find the gradients for it's not that it's hard to find the gradients. We like stochastic gradient descent finds the gradients. It's just that the gradients get smaller and smaller as you get into the layers more to the left, because most of the change that you can make to the gradient is in the last layer. or to the cost function, I mean, is in the last layer. So then we learn this really cool trick called convolutional neural networks, or convolutional layers, which is cool if you're doing image recognition, like we have been doing, but we were doing this just to learn how to make neural networks. So I don't want to implement this because it doesn't transfer over to text. But the idea is you're trying to, the thing that the network is trying to do is recognize features. Like the point of making the network deep is that you want the first layer to recognize features like loops or straight lines or things like that, and then the later layers to combine features together into concepts like the number 2 and the number 3. And so instead of making the feature detection layers, or the layers that your intention is for them to detect features, instead of making them look at the whole image and try to learn anything, the idea is to make them look at just a 5 by 5 pixel block and see if there's a loop there, or it's whether it's trying to find a loop or something else, a straight line or whatever, is not programmed in. It's not hard coded, so it'll learn what types of features that it's looking for. But yeah, let's say it's looking for a straight line. So this is saying, look for a straight line in a 5 by 5 area right here. And then you could have another neuron that looks for a straight line in the 5 by 5 area right here, and another that looks for a straight line in the 5 by 5 area right here. And then the cool thing you can do is, since the point of this layer is to look for straight lines, you can have the same weights for all of the neurons, so that if it's looking for a straight line, it's looking for a straight line anywhere in the image. So that has two purposes. First, it makes it understandable what the network is doing. Like, you're kind of forcing the network to do the thing that you want for it to do, which is look for straight lines, or look for curves, or look for loops, or look for whatever it is that you want it to look for, or whatever type of thing it should be looking for. So you're, on the one hand, by forcing the weights to be the same for all of the same 5 by 5 areas, you're forcing it to do that. You're forcing it to search for features, and you're forcing it to know that it doesn't matter where it finds the feature. They're all, it counts as the same either way, wherever it is. So on the one hand, you're forcing it to do something in a specific way. On the other hand, the number of weights is really small. It's 5 times 5, so it's 25 extra weights to do all of this extra work. So this is an example of the 5 by 5 weights if you plot them based on the size of the weight. So you could think of this like, these are really weird. If you had like a black line in the middle and white everywhere else, that would mean it's looking for a horizontal line. This one is kind of looking for a diagonal line. This one's kind of looking for an angled line that's not fully diagonal. But anyway, it learned these. So these are like magic learned features that it thinks it needs to look for in order to detect. In order to classify digits. So yeah, it gets a bit more complicated with pooling layers and stuff, but that stuff doesn't matter for what we're doing. And then the rest of the book is just talking about, in general, how neural networks work and what the history has been as of writing, which, you know, the history has changed a lot since the writing. So interesting history, but not super applicable to me right now. So we're done with this book. So what are we going to do now? My plan for right now is to take the first step to working with text. So I know that there's all of these neural network techniques for working with text. I don't know any of them. I've heard recurrent neural networks are a good start. I know that transformers are eventually what we're going to want to make a large language model. And I don't know how either of those things work. So my goal right now is to just really stupidly apply what we have to text without learning anything new, and see what that gives us. And my guess is it's not going to work very well, but let's just see how far we get doing that, and then maybe we'll learn something about why it doesn't work well. Or maybe we won't, but anyway, that's the first step. So the idea here is we're going to have our right here. We're going to have our ReLU hidden layer. We're going to have our output. And we're going to have our input. Draw some arrows between this. So this is what the neural network's going to look like. So let's say 30 hidden neurons. I don't know how many we're going to do. The output is going to be well, okay, so here's what I'm gonna do, and I know this isn't a good way to do it, but this is the easy way to do it that I can think of. It's gonna be a character by character output. So the output is gonna be one character. Which you can do as a not software, softmax of I don't know, 26 times 26 plus a few text, a few punctuation characters. So or 26 English letters plus 26 capital letters. 26 plus 26 plus, let's say, 5, let's say 8, just to make it a nice 60, 8 punctuation characters. So this could be a softmax of 60 different choices. The input, basically each character is 60. So we'll do, I'm not sure how to write this, but like x times 60. We'll see how many we can fit. So it's like if I give you 5 letters, if x is 5, can you tell me what the 6th letter is that's going to come after that? That's the idea. So, you know, maybe we'll have 60 letters, or I don't know how much, we'll just see how big we can make it. So if I did 60 times 60, that would be 3,600 neurons. We've been doing 784. So yeah, we'll just see. So this is the plan. We have to change a few things to get this to work. Well, maybe we only have to change one thing really, which is the data loader. So we need training data. But the training data is going to be really simple because it's just going to be text. And if X is 5, then it's basically sequences of 5 letters. And then, so the training is just tell me the next letter. Here's 5 letters, tell me the next letter. Here's 5 letters, tell me the next letter. And then when we want it to generate text, we can just give it 5 letters, ask it to tell us the next letter, and then take that and put that in the input again and ask it to tell us the next letter again, and then keep doing that. So even though it generates only one character, we can just make it do it multiple times to generate words and sentences, and we'll see what it actually generates. Maybe it'll just output the same letter over and over again or something like that. But yeah, so that's the idea. So for fun, the text that I'm going to be using is Final Fantasy dialogue. So I grabbed some text from the game. This is like a transcript of all the dialogue from the game Final Fantasy VII. This is going to be my training data. So if this works, we're going to have a Final Fantasy bot that can just output dialogue that's kind of like Final Fantasy. So let's find out if it works. Let's call this ff.txt. We're going to have to update our data loader, or maybe we'll make a different data loader. So here, this is just called data loader. Why don't we call this mnist data loader. We'll make a new thing called Final Fantasy ffdataloader.py. Right now it's doing the same thing as the mnist one. Load ff data loader. So we don't have images and labels. We have, well, we can just call them images and labels. It doesn't make sense, but we'd have to change all the rest of the code. We'll probably do that eventually, but let's start by just making this work. So to array. Okay. First things first. Why don't we take a look at the text that we have and see what it looks like. So Python load text from file with open ff.txt as f. read print len of text. Let's just make sure that this is working. FF data loader. Looks like 400,000 characters. Now I'm curious, how many unique characters? 87. That's more than I expected. How did we get so much more than 60? Well, why don't we print them and see? So we've got new lines. We've got a bunch of different punctuations. Spaces. We actually have more punctuation than I expected. What if we made this a... Can I put it into a counter? From collections import counter. Why is it deleting my import? I'm using it right here. Oh, it's just moving it up. Okay. Hold on. Let's. From pprint import pprint counter. This just means pretty print. Okay. So space, a bunch of lowercase letters. We've got dot, colon, new line, quote, question mark. Oh, numbers. That's what I was forgetting. Numbers adds an extra 10. So that would put us to 70, and then there's just more punctuation than I expected. Okay, well, let's just live with it. Maybe we could do something to strip, you know, the characters that barely ever appear, like the tilde and semicolon, if we need to, but for now, let's just live with it. So, can I put this in dark mode? Yeah. Okay. So this is gonna look like this. We don't need pprint, we don't need counter, we don't need mmist. We don't need nm data. All images, all labels. Yeah, okay. What was tr? Oh, okay. This was loading from this. So, so in our case, we're going to, it's all going to come from the same source. And then this we're going to have to change, obviously, to do 50K doesn't apply anymore. We'll have to have a different way to split the training from the validation from the testing. It's still going to be something like take the last 20% and that's the training data. Okay, so we've got the text. What do we do with the text? We need to split it into chunks of the right size. So why don't we make a variable up here? Cars, I guess. We can start that at 10 and we can change it as we go. So just to check, I don't remember, it was around 90. Was it 87? Need to check again just to get the right numbers. Print len of set of text. 87. 87 times 10. Why did I need a calculator for that? So that's 870, which is around the same size as the inputs to our current neural network. So this should be fine for now, and we'll change this. We'll see how, we'll change it and see if it does better with more or less. Okay, so that's the text. All images, so image would be where it's coming from, which is interesting because it's kind of the definition of image in math, so in a way I don't have to change it. Or is that pre-image? Math image. No, that's not. Yeah, this is what I want, image mathematics. The image of an input value x is the single output value. Okay, so I have it backwards. Image is where it goes, so I should change these labels. Let's just call them input, output. Input, output. Then we'll have to change everything to make that work. So all images would be all sequences of 10 characters. So for I, or maybe just while I, or while for I in range len of text minus cars. We can add dot append. Basically, let's just do dot append. I don't want to call it images. These should just be called all inputs, and these should be called all outputs. So all inputs dot append text I to text, or to I plus cars. And then what's the output? The output is the letter that comes right after that. So let's open up the Python interpreter and just double check that. So A, B, C, D, E, F, G, H, I, J, or yeah, A, B, C, D, E, F. And then let's say cars is 5. So I would say from 0 to 5, that's 5 characters. And then I would say the 5 That's the character after. Okay, so this looks like it's right. Then training data would be you know, the first 70% here, or yeah, 70%, 15%, 15%. We could do that. First 70%, next 15%, next 15%. So this, instead of going to 50K, you would go to len of self dot all inputs times 0.7. And then this is, you start there and then you go up to 85%. And then finally this one, you start at 85 and you go all the way to the end. Okay. All right, now my inputs are strings, but I need to vectorize them. Which means like the letter A up. Or let's say the letter B looks like this. So that's for one letter, and then if it's like BC, then it just keeps going. 0, 0, 1. So it just becomes one longer vector. Okay. So it's 87 characters. That's what our output should be. Vectorize. We're only going to need one of these, so let's just call it vectorize. It takes text and returns an ND array. it should be zeros, yes. Everything is a zero except the one place where it's a letter. So this is what it looks like when it's I mean, it's not 10, it would be 87. Times however many letters are in text, so 87 times len of text. And then you have to put ones in the right places. So we need to have an encoding. This is our encoding from text to vectors. How do we decide what order they should be in? So I could just use, what's a good way to do this? I could use the frequency. It doesn't really, it doesn't actually matter what order they're in as long as I keep the same order. When I'm encoding and decoding. So def encode string to int. This is really just character to int. And then we're going to have a decode. So I think I'm just going to start by building this map. Okay, here's the thing I'm struggling with. I have to read the data in order to build the encoding because it depends on what characters show up in the training data. So I'm going to read the data in order to define my encode and decode functions. So yeah, then I just need a way to map. I just need an ordering of the characters. So basically yeah. So here's my set of characters. Turn that into a list. Let's save this list. We'll call it mapping, or all characters. Then to decode, you just return your position in all characters. To encode, you return your, or I said that backwards, but to encode, you return your index. So does that even work? A, B, C, D, E, F dot index of C. Yes, it's just that I need to do +1 in order for there to always be a 1. So return 1 plus this, and then subtract 1 here to find it in all characters. Okay, so when you vectorize, you do for C in text, let's do I, C in enumerate text. You're gonna do I times 87 you want I to start at 1, so I plus 1 times 87 that tells you which letter it is, or like letter 3, letter 4, letter 5, which of those it is. And then to find where it belongs in there, you would do encode. Let's see. Okay, is it possible that this makes any sense yet? Actually, can I import FF data loader? No. Give me the first training example. Let's just and then exit. Python main.py. No module named data loader. That's true. Oh, we were importing it in network. So because we're defining this thing. All right, well, why don't we make a data loader? Move this into here from, or import NumPy as NP. You can import these types. Input, output, data. Okay, that's a real error. So actually, you know what? This shouldn't be +1. This should start at 0. Slice indices must be integers. That makes sense. Because I want it to be a percentage, but it has to be an exact percentage, but I can just round down. I can do the same in all of these. Okay. So, oh, there's a 1 down here. Okay. Well, I guess the first issue is I didn't vectorize the input. Did I just forget to do that? Yes, I just forgot to do that. So vectorize both of them. Vectorize both. So now if I run this, 870 is out of bounds for axis 0 with size 870. That's because of my +1, I think. So, oops. All right, so there's a 1 over here, and then this should be a huge dimensional matrix, or it's not a matrix. It's kind of a matrix, but it's a vector that represents a matrix that should have a bunch of 1s. And we should be able to decode it. Vectorize, step unvectorize np.nd array. Which should just return string. So how do you do that? Every 87 characters, you check where the 1 is. Then you turn that back into a letter. For I in range v dot shape of 0 divided by 87. So this is going to be 1 character per, or this is going to be per each character. Then I want to know v from I times 87 to I plus 1 times 87. I want to know where is the 1 in here. So we'll just go for j in range v, or range 87. If v b of I times 87 plus j equals 1. We'll have to come back to this to do what if it's a softmax output. If it's a softmax output, then it won't be exactly equal to 1. We'll want to take whichever one is the biggest. But I think our code already does that somewhere. We take a max. Somewhere in here, right? Argmax. We do that when we validate already. Okay. Okay, but if it's equal, then let's set our ret here. Ret plus equals decode j. Break. Because now you can go on to the next letter. Then at the end you return ret. So we should be able here to say load data loader, load unvectorize, and then print unvectorize. Print the big complicated thing, and then unvectorize the first part, the input, and unvectorize the output. Didn't work. I'm guessing we're just off by 1 somewhere because it looks close-ish. It's the right number of characters. MNIST data loader, go away. FF data loader. I'm doing the -1. I wonder if I should just not do that at all, and then not do it. Where was I doing it? I don't know if I was doing it. Not right either. Where was I doing it? Here, -1. This looks really close, obviously. What's with this quote? And what's with M? Because the actual first... Oh! That's just correct. Okay, that's correct. Okay. So that's the first training example. Give me the shape of each instead of instead of actually printing it. And then this time give me a random example, like 15,000 deep. Question mark, new line, Tifa, colon, space, so, and then M. So I'm guessing this is going to be like something, right? Question mark, new line, Tifa, Tifa, so, meh. Huh. It doesn't think this exists. Unless it's so M space? No, it's not that. Well, it's not good that it didn't find that one, or that I can't find that one. If I go back by one. Still think it thinks the output should be M, but that doesn't look right. I mean, we know the output should be O at this point. So am I doing something different in Yes, I very much am doing something different. I'm not taking I into account. This needs to be I plus cars. Oh, and that's correct. Okay. Okay. So what if we just start training? What is it going to look like? So 870 is the number of inputs. 87 should be the softmax output. Just go. What's it going to do? %? That seems crazy high. Maybe just like knowing when to put like the letter E and the letter A. I mean, this just seems so high that it gets the next character correct on data that it's never seen before half the time. Okay, I have to stop it because I'm really, and I haven't tuned anything yet. I'm really curious, what is it outputting? what's a good way to do that? I think I have to build the whole recursive re-inputting the thing into itself if I want to watch it generate text. How many training examples do we have also? We must have way more than before. Though we managed to do 5 iterations, it looks like it would have only taken like 6 or 7 minutes to finish training. But yeah, why don't you do 3 epochs? And then don't just validate. I want to actually like get to use it once it's done. So net dot, what do I even call it? Like, what is using it called? I never actually used the other one. Apply. So it would be net dot apply. Input. I actually don't even remember how to do Python input. Python input. Write something. A equals input write something. Colon new line. Write something. Blah. Why did it say write something multiple times? So, and then A. Okay. Okay. So input, let's just say prompt, colon, new line. And then take the first 10 characters of that and encode them. Vectorize them, I should say. I have to import that from so take a prompt, and then let's just do this infinitely. You take a prompt, and then you or you do this part infinitely, and then you have another while that you do like 100 times for I in range 100 to generate the 100 next characters. So the prompt you only take once. instead of 10, I want to take cars, which I have to input from data loader. So we have the prompt. We want to generate 100 characters. So this will generate the first character. C equals this. And now prompt is going to be equal to plus equals C. Prompt equals prompt. Just the last 100 characters. Negative 100. Does that work? Python ABCDE. -3. No, that does not work. What if I put it here? Yeah, that's the last. Okay. So 100, give me the next 100 characters is what this is doing. I would love to print them as I go, but let's not do that yet. Let's just print them when we're done. Yeah, we can print them as we go. Text equals prompt. Text plus equals C. Print text. It would be cool if we overwrote it as we printed it. There's no easy way to do that. We'd need curses or something, right? Python overwrite text. Output. Oh, yeah, I could print without a new line, right? I didn't think of that. Carriage return returns to the start of the current line. But if I just have nothing as my end of string, if I just did print C end equals nothing. Then I wouldn't need the text. What does it do if I have less than the amount that I'm saying to take from the end? It still just works. Okay. I guess let's see if this works. I don't think it will. %, 45%. 6.8%. Now I have a prompt. So let's prompt it with who's a character with distinctive Barrett. Barrett. 1, 2, 3, 4, 5, 6, 7, 8. 2. Enter. What's the problem? I couldn't add C to my prompt. I forgot to decode, probably, right? Unvectorize. And then does apply, so not only unvectorize, I also have to argmax it first. Yeah, np.argmax. Okay, let's try it again. Okay, actually, let's just do one epoch because I just want to see if it crashes. I don't need it to do a good job yet. Barrett 2. Tuple index out of range. Oh, argmax is just giving me a number, which is kind of cool because that means I can just use decode. Which is kind of interesting. Because argmax is telling me which number is the biggest, which index is the biggest. It's not converting it into a vector where that's a 1 and the others are zeros. Barrett 2. Okay, what about cloud? I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm star. Huh. Okay, hard to tell if it's working. I guess I could try giving it something that it should know. Barrett. You. How about Tifa dot 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 dot. It thinks there's more dots. That's like, that's kind of evidence that it learned, because that's right, right? Like, it knew that if you have a bunch of dots, you probably want a bunch more dots. So I should actually get it to print, because I don't know what it's not easy to see what the first 10 characters are. So start by printing the prompt with end equals nothing. Print a space in between also. That's obviously not how you do that. Clear this. Let's let it train a little bit more. 3. And then what we should do is reduce the training data and the validation data and see if we can find hyperparameters that do anything helpful. .4, 46.5%. Oh, final accuracy 45%. Prompt, Barrett 2. So it's starting with a bunch of spaces, right? Or it started with a new line and then a bunch of spaces. I should have a new line here also, just so I don't confuse it with but yeah, if I take like a longer string, which is longer than it can fit in its context, it has a context window of 10 characters. Oh, no, okay. What I meant to do here is not print. So here I need to take the first 100. We'll do that at the beginning so that we always know that we can do it here. And why am I taking 100? This obviously needs to be cars. This is 87 times cars. I screwed it up. What am I doing wrong? My prompt is not the right size. I would rather take the first 100, the first card, or yeah, that's what I did wrong. That shouldn't have been 100, that should be this, and I'm going to take the first few characters instead of the last few. So the last few might make more sense. Doesn't really matter. Yeah, actually, I like the idea of taking the last few, now that I'm thinking about it. So, like that. We'll try it like this first and then see. So this is too long of a prompt. Oh my god. So it only took Barrett : co, and it said come be some here and the can the. That's amazing. It kind of, I don't want to say it makes sense, but it's like, it's words, and it has no concept of words built in. What if I just say, spoilers for Final Fantasy VII, by the way. I'm just trying to find some random words. How about looking for thing to sow the she. That's so cool. Materia is a this, and the can C pen for here. This is so cool. If I don't put enough characters, it'll break, right? Yeah. Okay. How should we fix that? So why don't we add 10 new line characters to the beginning? Or not 10, but cars. So I can write this in an easier to read way. Prompt equals, well, actually, it's fine like this. So take the ending of them. But I want to see if I can train it better first. So training, I don't know how many training, print len of data dot training. End of testing, end of validation, and then exit. $300,000, 67,000. So let's just take the first 10,000. Or let's take the first 50,000. Yeah, we'll do kind of, this is the same as what we had before. But obviously you put the colon at the front if you want the first. Okay, so give me the first whatevers, and now this should train about the same speed as before because it's about the same size network and about the same amount of training data, before being like when we were doing image recognition. And then obviously don't exit, that's not gonna help. And with this amount of training data, I guess our hyperparameters should be more comparable. So we only really have two hyperparameters, which is the regularization, the lambda and the mu. Lambda, unfortunately, is dependent on the amount of training data, and this is screwed up also because I don't have the right amount of training data here. But that means I'm not going to be able to find the right lambda, because it's not going to be the same number when I get to the bigger training data size set training. Yeah. So can I at least find mu? Can I find a good mu? How about 0.2? So we got to 42 before, right? We got to, oh, final accuracy 40. Oh, but as we were going, we got 42. It's about the same, it seems. Maybe a little better, hard to say. It seems better. So is even more mu even better? What if we go to 0.4? Tofu gonna be a thing. The was it. It's so cool. It's so cool. Does 0.4 do even better? Five iterations, we're at 41.3 before we were at 40.4. So possibly it's doing better. Seems less stable, but it gets higher. Yeah, 44.5. And Ada did drop. So Ada actually seems like it's at the right number because it worked for a while and then dropped once it stopped working and kept going up. I wank that the WASP to the Sure and the Donner that the WASP to the Avalanche is not. It's so cool. Oh, what if I do something that's not enough characters? It still works. You don't even think. And the planet. Use my material. That's weird. Why didn't it start with use my? Oh, probably because I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I was trying to get it to say materia or some other word that only appears in this. Like, what if I just say, I'm joining Aval. Yeah. Avalanche. It knew. It knows. It learned. It's so fucking cool. So mu seems fine. Learning rate seems fine. Regularization, we don't know, but that's really hard to do because it seems to depend on the size of the training. So, so I want to try to give it a chance. Is Lambda supposed to go up or down when you have more data? Michael Nielsen, deep learning. Regularization parameter 1000. Since we changed the number of training examples, we should change Lambda to keep the weight decay the same. So when you have less examples, you should make Lambda smaller, which means I should make Lambda bigger. I have, so we went from 50,000 to 300,000. And I should make it bigger, so I should make it 6.6 times bigger, so times 5. So it should be around 31. Why don't we try putting it around 31? Also, the validation and test size are so big that that's going to be taking a long time just doing the forward inference just to know what our percentages are. But here we're starting at 43.5 in the first epoch. Already at 46 by the second epoch. I really want to just let this run for 5 minutes and then then ask it some Final Fantasy stuff. Soldier, that's another good word. We've got some character names: Cloud, Barrett, Tifa, Red to 13. They talk about Spirit, they talk about Materia. They should talk about Materia. Materia hasn't worked so far. But yeah, they talk about Materia. They should talk about ancients. I guess they don't mention it that much, only 44 times. Oh, it looks like we've stopped learning. Hopefully Ada goes down first. The way that our decay schedule works is it can only go down after 10 epochs of not learning. So it takes a long time before it decides to go down. We've got location names: Cosmo Canyon. Only appears 17 times. The planet, they love talking about the planet, 131 times. There's a guy called Bugenhagen, 109 times. Describing the way the game works. I think this is kind of a data error, actually. I don't think Cloud is the one who says these instructions to the player. Sid and Vincent, other characters. Vincent has barely any lines. Genova shows up a few times. I think Genova only has one line. It doesn't show up as a line. Sephiroth, that's another character. Yep. Oh, we got to 48% when I wasn't looking. Choco Bill, I don't remember this person. Shinra, forgot about that. That's a company name. Shows up a bunch. Shinra Incorporated. Shows up a few times. %. We're still learning. Our Ada has never gone down. We never had to decrease the learning rate. Though we probably should, because we're going down a lot. But that's not how the decay schedule decides. Avalanche in all caps shows up 46 times. Sector 7, that's another location. There's a few sectors, right? There's Sector 6, and Sector 7. Sector 7 shows up more often. Sector 8 shows up twice ever. So we could try saying sector, and we should expect it to say 7. Because that's right most of the time. But just the fact that, like, the game says Sector 7 and it says Sector 8. So if I say sector and it gets it right, you know, like, what am I trying to say? It can't really get to 100% accuracy because there isn't a unique answer. It'll fail on some prompts. Okay. Barrett. What is? What is the stall, the stall, the stall? Avalanche is. Avalanche is the stall, the stall. That's interesting. How about cloud? Classic cloud. What does NPC say? What's the most NPC thing to say? Rightly, it's a lot of dots. NPC. Huh? NPC. The stall, the stall, the stall. Interesting. What is it? What is it a now the stall, the stall? What does that mean? Does that mean we overfit? Because it thinks the stall is the answer to everything? Oh, cloud. Oh, cloud. I don't the stall, the stall, the stall. The. How about sector blank? Sector the stall. Sector 7 as a person. I don't go the the stairs, the stall, the stall, the stall. That's interesting. I don't really know what it means. It seemed like it overfit. And regularization is supposed to help with overfitting. So is dropout, but we're not using the dropout. Regularization. Trying to remember, is bigger lambda or smaller lambda better to avoid regularization? So when you regularize, we subtract away lambda. So bigger lambda should help avoid regularization, because bigger lambda means you don't get to remember as much of your weights. So we could try boosting lambda. Multiply it by 2. We could do fewer epochs, like it wasn't learning that much after a while, it seemed. Cloud. Hid are the stove, the stairs, the stall, the stall. The crazy thing is it's always saying English words, right? And it doesn't know words, it just knows letters. Okay. Why don't we try this? We've doubled the lambda. We've got 3 times less training to do, so hopefully it doesn't take that long. Oh, actually, one more thing. Let's add more neurons in our hidden layer. And why not? Let's just have 2 hidden layers. Is it even able to work? The other thing we can vary is how many characters are in the context window. That might have been too much. Okay, let's cancel that. A single 100 neuron hidden layer, so that's more than before. It's a lot slower, huh? It's not, it doesn't even seem like it's 3 times slower. It's more than that. .6 after the first epoch. So more neurons helped a lot. Or possibly more regularization. No, regularization, yeah, we don't know. We tried both at the same time. How fast does it go up after the second epoch? It's taking 40 seconds per epoch. Oh my god! 49.97%. That's kind of crazy. I actually kind of want it to just do 3 epochs because it's taking too long, and I'm also kind of scared of overfitting. We crack 50%. Okay, let's clear this. Let's do this again. This should take 41 times 3 divided by 60. 2 minutes. And then I think we'll call it there for the day. So we'll play with it a bit and see what it looks like, and then we'll call it a day. By the way, this is way better than I expected. I thought we were going to try this, it wasn't really going to work at all, and then we'd be like, this is why we need whatever the new techniques are that we're going to have to learn next. But we're printing English words, and we lost this in the last test. Maybe we'll see if it comes back, but we were able to also remember concepts from the training data like avalanche and I don't remember what else, but let's see what does it look like when it's an above 50% accuracy. Final Fantasy VII dialogue predictor. crossing my fingers for 50. 50.5. And then the accuracy, it's using a different thing. It's comparing against a different thing for the accuracy. All right. What should we try? How about I'm joining Avo. Ning avalanche on the sea in thing to she something to she something to she something. Uh-oh. It's, hopefully it doesn't say that for everything. Cloud. That's good. That's lore accurate cloud. Sephiroth is it and the thing and on the sea in the thing to she something. Okay. To she something. I wonder if it is overtraining or if it's just because the context window is so small. It's kind of like a Collat's conjecture thing where whenever it gets to thing, then it wants to finish, or whenever it gets something, because this is already 10 letters, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then with a space before or after it's 10. So whenever it says something, then it's stuck, and that's not avoidable. That's like, it's not overfitting or anything. That's just because it says the same answer every time it has the same input, and whenever it gets to something, it has to say the same thing. Does it know the right sector? I live in sector. Sector 7? Yeah, 10 is a brutal number of characters, because it's really hard to get it to say something like related to what you're typing, because it can only get like one word of context. In sector. In sector space. So I didn't learn sector 7. It looks like it did learn avalanche. In Ava. In Avel. In Avel. There it goes. Does it know the characters' names? My name is Sephi Roth. And then Cloud responds with ... That's so cool. Okay. I said that would be it, but I actually want to try giving it more context and seeing what that does. So what if we triple the context window? Is everything gonna break? Obviously it should be slower to train. How much slower? We doubled the size of the first layer, basically. Doubled the number of weights. Or maybe we more than doubled the number of weights, actually. Yeah, we more than doubled the weights. We doubled the number of biases. No. There's still 100 biases, because you have one bias per neuron. I think we only doubled the number of weights. It's going very slow. Slower than I would expect. Did I say? Oh, I tripled it. I didn't double it. So equals 87 times 30, 2,610. And that's times 100, because that's the number of neurons. So this is the number of weights. 44.5 on the first epoch. That is higher than before. It's like 1% higher than before. Although the validation, the comparison is not apples to apples. It's harder. No, it should actually be easier to predict the next letter when you have more context. So I guess in that sense it is apples to apples, because we're still just trying to predict one letter. But now we have more information, so it should be better at doing it. So how long does this take? 114 seconds per iteration, which is about 2 minutes. Per iteration, so this many seconds. Can I do that? Oh, that's so cool. So 5 minutes. We're maybe halfway. Maybe we have 2.5 minutes left. And this will be it for today. This is so cool. It's just so cool that this works. We built a neural network for predicting. Oh, that's interesting. That's not as good as before. We were at 48 after the second epoch before. So I don't know if we're even going to crack 50. And I wonder what impact it's going to have on the prompt. But yeah, it's like the exact same code. You put in as inputs image data and it can classify them. You put in as input text and it can write English text for you. It's pretty crazy. All right, neural network, wrap this up. I forgot to try to talk about the city or planet. How often does city come up? Not that much, but planet. Still not that. I mean, that's a lot. 131. Shinra? Shinra shows up way more. Let's talk about Shinra. And then the characters, like Cloud shows up 1,000 times. Barrett shows up 500. Yeah. When Barrett swears. Okay, final accuracy worse than before. Let's see. What is a classic Barrett line? ... True. Cloud is the same. I'm joining Ava. I'm joining Avalanche! Exclamation mark. Cloud ... Is that a full, like, does that line actually happen? I'm joining, no, but I'm joining soldier with an exclamation mark, and then Cloud responds, does happen. I live in sector. I live in sectory. It manced for a something to the Stowe Stark. So it's not English words anymore, which isn't necessarily bad. It's hard to it's hard to say what's the difference between overfitting and or like underfitting versus being creative. Tifa. Everyone's classic line is to not say anything. And you can see in the dialogue that that's right. I'm going to equip my something beyond me the materia here. I was trying to get it to say materia. What's wrong? What happened? Hello, my name is a make to the promised land. And this is the should to the promised, to the seep to the Surrey. I like this one better than the other one. It's more interesting. I'm going to go talk to Red 13. I don't know the Sur in the Reach. I work for, I wanted to say Shinra. I used to work for, it's hard to come up with a prompt that even has 30 characters. What if I lift something directly from the text? It doesn't say the full rest of the line. It's interesting. I wonder if it would if I trained for longer. If it would memorize all of the text that's in here at least. I guess we could also calculate based on the weights whether there's enough storage space to even remember this text. Probably not, because it's a lot of text. Says that. Very cool. I just want to keep playing with it. I kind of want it to, I don't know. I guess we shouldn't expect to see it do anything really smart. It's kind of amazing that it can do even this. It makes up words, but they sound kind of like words, like main. Surrey. Sums. I wand the was a wrong on the sir in the say. It loves saying sir. Yeah, that's what it says for everybody. The sir of the want to the... Yeah, it's kind of interesting. The 10 character context window version was better at using words that are actually in the text. And this one is making some stuff up, like Surrey, that shows up nowhere, but it loves to say it. How often does Promised Land show up? 28 times, but it loves talking about it. What about life stream? 17 times. I will return to the phase. Return to the life. Return to the life stream. It's close, Mr. Bugenhagi. It's not very good at, like, my trick of having a bunch of new lines before has not been very good at telling it to start here as though it's a line. I think I could fix that by adding training examples that are not exactly 10 long, but that start at the start of the line. Like, I don't know where it consistently gets this thing where it needs to have multiple colons in a row, and that never happens. Okay, well, that's going to be all for now. Thanks for watching, and I hope this was helpful.